So that's the same as 379 times 5.615 is 6,000, no. 16.
1600.
Can you give me a number? I think it's 21 something, but
Yeah, 21 straight line.
2140. Okay. Okay. That's the GR. Okay. Okay. So now let's conduct, we're going to conduct a gas condensate in the PVT simulator, a constant volume depletion experiment. Okay? And we're going to keep track of let's see here. Okay. So if the well stream we're interested in from the CVD test, okay, from the CVD test, you basically have two phases in the PVT cell. You have some oil and you have some gas, and then you've just removed some of that same gas, right? That's what's been removed. And we know basically how many moles of gas have been removed, right? And we know and we can ask it for the composition of that gas in terms of the SG lump component and the SO lump component. We can ask for the mole fraction of those two, and it'll give it to us. But if we're interested in the GOR of this removed gas, right, then this term here, okay, for CVD gas, NG is going to be 2140. NG is going to be just YG, okay? Because the moles is the moles NG times YG, right? Divided by the moles of oil is NG times YO. But of course that how many moles you remove doesn't matter to the ratio. Okay? Yeah. So all we need to have printed from our experiment is really the mole fraction of either the surface gas or the surface oil, because that you can just rewrite as 2140 1 minus YO over YO, right?
On the equation 2140 Ng by NO, did you miss molecular weight divided by density?
Okay, yeah, we need this term here, which is going to be rho O to MO. Yeah. Right. Okay. All right. So we need to print the molecular weight and density of that component. All right. Okay, so let's create a PVT experiment. We can do that. Have we changed this data set here at all? I think that's all in the Excel file still. Okay, so just continue with this. We'll make a new experiment. Okay. Okay. Let's see here. I want to. What we want to do here is have our reference pressure and temperature, the initial, in the reservoir. Temperature is 200 Fahrenheit. Okay. And in fact, we can say that the PVT cell contains as much material as the reservoir model, if we want to. I mean, it doesn't really matter, but if we want to look at recoveries, so we could look at the output of here just for the fun of it. We can initial, and we can say that the initial hydrocarbon volume is that. Okay, 16497,000 barrels. So this is basis 1647 barrels. Okay, at that condition of 5,200, right? 16497, 16497. That. Okay, and then we'll do, at each stage, we'll have a pressure. And let's see here. So what do we want to have? We want to have how much gas was taken out, moles of gas removed, and we can take that in standard cubic feet. Okay, now that's going to be that's going to basically be this number here. Okay, and of that, what's removed, we want to know the composition of what becomes surface gas and surface oil, right? But that's simply the mole fraction of surface gas and mole fraction of surface oil, Sg and So, that we defined. Okay? It'll take the actual full component slate and it'll use those recovery factors and tell us what's the mole fraction of Sg and the mole fraction of So. But in reality, we only need one mole fraction, right? We only need the oil mole fraction. So I'm just gonna print the Y, that's the mole fraction of that, of Sg, and it'll be in fraction instead of percent by default, so I'm not going to put percent. We'll be using that to multiply, except that should be So. I'm going to use So. The mole fraction of the surface oil. What else do we need? We need the molecular weight of the surface oil, right? We need the molecular weight of the surface oil. It'll also give that. It'll actually calculate using those recovery factors. Now the problem is it's not going to give us the, I can't ask for the density or specific gravity. That unfortunately doesn't come automatically. So we're going to have to do something else there. Okay. Exactly how to get that I'm not quite sure, but we're going to have to take that composition and save the. We want to save the take the whole gas composition, and then if we extract only the C5 plus part, that's about the only way to get those densities. So I think or let's see here. What was the saturation pressure? 3480? Okay. Okay. So here we'll have how much gas is being removed each time. Here we'll have the mole fraction becomes surface oil. We have the molecular weight, surface oil. And then the density. Let's see here. Let's see if we can try to extract that. The molecular weight, what it's going to do of this, it's going to take this is a component. It's going to, and we're of the gas. It's of the gas phase. So this is of the gas phase. It's going to take in the simulator, in the PVT simulator, it's going to take the gas composition, calculate the total mass. It'll take the gas composition, times the recovery factor of that particular component. That's what's going into the surface oil phase, times the molecular weight of the component, divided by, this is the total mass of that surface oil component, times the moles, which is this. Okay? That'll be the molecular weight. The density of that surface oil that evolves from the removed gas is approximately, if you use ideal volume mixing, then it would be, then we could use the specific gravities of each of these components. And let's see here. That would be the same as this here. That would be the mass. That would be the same. Here. And then it would be divided by the ideal volumes, okay, which is these are the masses divided by these liquid densities for each of the components. Okay. This represents the sum of the ideal liquid volumes. This is the sum of the liquid, basically of the masses that become surface oil, right? This is the fraction here of what's removed as gas that turns into surface oil on a molar basis. And multiply the molecular weight, then you get the total mass that becomes surface oil from reservoir gas. Now what we're really wanting to do is that we're wanting to convert to a volume here, right? That's what we really want. So what we'd really like to know is what is the surface volume here per mole of that. That's what we'd really like to know. But that's equal to this over this, right? That's volume, surface volume per mole. But what is that? Well, if we take that divided by that, then you see this term cancels, right? So that if we call this, whatever you want to call it, this term here, it's usually called molar volume. This term is usually called molar volume of surface oil coming from the gas. That would be equal to that. And that's equal to this term here, divided by that term there. Right? Yeah, I don't really see any way to get this clean way. Let's see here. Yeah, I think the only way to do it, because in essence we need to pass the removed gas well stream because in the simulation what it's taking the removed stream and putting it through this process, and we really need to do that with the experiment here to get the amount of gas and oil. But and we can get the moles that turns to surface gas and surface oil, but getting the volume of the surface oil, it's not trivial, because you have to basically process out from the removed gas the composition of this surface oil and then take it to the equation of state to get its volume. That's what really has to be done to do it right. And so we can do that because what we do is we take the equilibrium vapor here, and we can store that removed equilibrium vapor, put it in a tank. We'll call it gas 5000. Oops. Gas 5. We'll put a tank there. It'll be another tank, gas 4500. Of course, these are all going to be the same down to the dew point. These will be tanks, so we don't really need those. But when we get down to the saturation pressure, which was 3480 approximately, or 34. 3480.8. And then for each one of these, we have to do a we have to basically extract out only the surface oil part by the split factors and take the resulting feed oil to get its density. That's about the only way to do this manually. So it's a real pain. Well, I can do it for one of them and then repeat it. So that's going to be, we're going to mix, and actually this, all of these are going to be the same here, so we can just start there, because all of these are going to be the same above here, same composition, right? So we can just take, and we can say multiply the components CO2, C7 plus 3. And G 480 by no, let's see. All we have to do is we have to multiply. We're going to get rid of all the light components, so that's going to be down to C. Get rid of the light components to C3. So that gets rid of all of those components. So now the tank, this tank G3480, has gotten rid of all of these light components. But we also have to get rid of this where's the lump commander? Was that in the file? Okay, these I didn't. Okay. Put those in there. So this, we have to, we've gotten rid of those, and we need to get rid of this much of the next component, 53.5. And that component's C4.6. 535, is that right? 535, C4, C6. Okay, so now what's left in this tank here is just the C. Yeah.
So I think the first one should be multiplied by 1, not by 0.
Well, what we're trying to get is we're trying to get this to contain only the surface oil part. So we're eliminating the light stuff by multiplying it away. Okay? So what we're left with is 46.5% of the C46 component and all of what is C7 plus. So we're kind of removing the light stuff here. Yeah. Well, but it's still left there. We're not doing anything with it. It just keeps what's left there. So now what we have left in this tank is just 46.5% of this component and all of the C7 and heavier. Okay? So now what we can do is we can just normalize that to 1, if we want to, and go off and calculate its density. Okay? So now if we just do mix G3480, and now it'll create 1 mole of that. It'll just normalize it. And then we can set up a temperature, 60 Fahrenheit, pressure 1 atmosphere, and then just do a flash. That will give us its density from the equation of state of that mixture. And then we're going to have to hand pick that density to use together with the molecular weight here. So it's kind of cumbersome, but this is basically stripping out the gas components. What you're left with, you do a flash at standard conditions. So this is going to give us the density of that oil. That'll be the same process that actually Sensor is doing in the simulator. It basically strips out the gas components, calculates times 379 to get the standard cubic feet, strips out the oil component, sends it to the equation of state, calculates the oil volume. That's effectively what we're going to do here. Now that's just for the first one. This has to be repeated for each of these. Okay? Pain. So let's just try it the first time for the first one and see how that works. Okay. And then we'll have to put that together with the molecular weight here. We've got the gas removed, which is the standard cubic feet. That we can also actually, I'm just going to keep this in moles, I think. Pound. Not sure how it's written. Pound moles. Maybe. Let's see. Okay, let's try that. See what happens. Like something. Gas removed. CVD, basis, stage, pressure, gas removed. Gas removed. Maybe moles removed. Yeah. Gas moles. Okay. Yeah. Gas moles removed. Okay. Try that. Gas moles removed. Maybe it's just moles removed. Yes. Moles removed. CO2. Okay, moles. Okay. Okay, multiply. I think it's multiply moles. Okay. All right, so we've got still got our $3480.8. Okay, we've got it's storing these tanks. This is the moles removed. This is the surface oil lump component and the gas. So if we multiply moles removed by that fraction, then we should get the moles of surface gas removed. I've got the molecular weight. You can see that's not changing very much of the surface oil. Then it goes in and it multiplies this and the 3480 by 0, and we end up with the composition here, except we didn't get rid of the CO2. This is strange. Equilibrium vapor. That didn't work. So it's not doing the. Maybe we should just see what we have in the way of when we get out of this. When we leave, let's just see what we have as a gas composition there when we finish. It should be storing this gas from here. Yeah, see, it's not filling that tank, right? 3480. Equilibrium gas. Strange. Why is it pure CO2? Oh. Okay. Okay, this is it has to look like that. It's making a new tank from the old tank. Before it was just making a new tank full of 1 mole of first component. So that's There we go. Now we got our gas. Get rid of the CO2. Down through there, we got a little bit of the C4, C6 plus left. We do a flash calculation. Should be a liquid. That results. Now we've got a little bit of a problem that liquid is splitting into two phases. And that's not good, because this stock tank liquid that it's getting, surface oil, is splitting into two phases. And now in the simulator, when it takes that oil, it's not going to do any flash calculation with it, because you're saying you don't want to use the separator flash. You're going to use the component split. So it's going to take that overall composition here, except, okay, well, maybe the problem is that it's got the wrong stuff here. It's not taking this. Okay. Okay, so we were using the wrong material here. Okay, I see. This should be mixed feed. Yeah, that's to fill the PVT cell with that. Okay. That's the problem. You see, it was not filling, it was not doing the flash with the stock tank oil. It was using the whatever was coming from somewhere else. So we have to change this here to feed like that. There we go. Okay. Okay. And it's doing still seems to get two phases. That's not good. Still. Okay. Do you all see the problem? What's happening is that it's splitting out the components that you say you want to be surface oil. But if you try to put that into the equation of state, it'll split into two phases. It won't be a surface oil. Okay? Now some reservoir simulators will actually try to do a flash of that, and others will just say, whatever you tell me is there, I'll consider it an oil. And they'll calculate kind of a pseudo oil volume. So the programs are going to give different results. And that's often a problem in using these split factors, or recovery factors, for a surface process, is that you don't get a kind of a thermodynamically consistent result. So what we're going to do now to avoid that is that I'm not going to let any of the C4, C6 go into the stock tank oil. It's making it too volatile. Okay? That's what I'm going to do is change that. So in the simulator, in the reservoir simulator, I'm going to change the recovery factors, wherever that input data set is. Okay, I'm just going to make this 0. So it's going to be a stock tank oil is going to be C7 plus. Okay, it's not a very efficient process, but it's for the sake of what we're doing, we're going to. So we're going to change this. We're going to have C4 minus, and it's actually going to be C7 plus, and C6 minus. Okay. Now when we rerun this simulator, is this initial fluid in place going to change?
No.
Not the reservoir barrels, but it's definitely going to change this 7228, right? So let's just rerun the simulator and see what we get. Yeah, so you got 11,000. You got a lot more gas and less oil, but this number shouldn't have changed, which it didn't. Okay. Okay, so now we have to go to the go into here, change our lump. We just change surface gas is we'll just take C46 here, and we'll just C7 plus 1, C7 plus 2, C7 plus 3. So that'll be what we define as surface oil and surface gas. Okay, and then we'll come down here. So now what we get in the way of surface oil will be different. Its molecular weight will be different. It'll be higher. And we'll get a different result down here. So let's bring all that in. That, place it, rerun this, US. Hopefully it's going to be single phase, what we end up with. So now you see it, this is still not right. Oh, okay, that's because we didn't change these. I can get rid of this line, right? Okay, now we got only the C7 plus coming here, and now we have its single phase, and it's actually doing what's called a negative flash. It's allowing it to do a negative flash. So I'm not going to let it do that. I'm going to force it to not allow negative flash. So what we'll do is that we'll write up here stability. I don't remember the on. I'm not sure what I have to go check the manual of this. Stability. Let's see here. Initialize stability. Here it is, stability on. So that means it'll never accept a negative flash. So I think stability on is the keyword. That stability on. All right, again. And you see now when it does the flash, it forces it to be a physical solution, which is and now you see that what we come in with is considered liquid, and this molecular weight should be the same that's up above, 133,663. is 133.66. But the density we now get down here, and that's 0.781 grams per cc. Okay, and then whether that changes much with the as it depletes this gas condensate, whether that changes much as you deplete, the only way to find that out is to take and redo this same thing here for a number of these other mixtures. Okay, so I can do a few of them. Do them all if we weren't getting tired. So I'll just go in and do some of them. We'll do 3,000, 2,000, and 1,000 just to get a feel for it. Okay, so let's see, we have to do it. It's just what's been selected. Do you know how this works? Whether it only take what's selected or not? Should we take a chance? That was nice. It worked. Okay, 1,500, 2,000, 25, 3. Okay, so we'll see whether that density changes much or not for these different ones. Okay. Okay, so we got 781, 776, 773, 77, 767. So it's not changing much, but at least we now know the magnitude of that change. Okay, so now the question is, if we take for this first mixture and see the CVD test here, can we get the same kind of cumulative gas produced at the dew point? I mean, first we have to get the same GOR. We have to make sure that we get the same GOR from the two. So the GOR from the simulator is 11,014, right? So let's see here, where's the pen? We get this to work, then we'll take a break. Okay, so the GOR from phase comp was this 2140. Right, and it was times basically the 1 minus mole fraction of oil, and then times that ratio of density to molecular weight in pounds per cubic feet. Okay, so 1 minus, and then we have to go to the Okay, 1 minus, this is the mole fraction, right? Becomes surface oil from the reservoir gas. So 6.6% becomes surface oil. 0.659. Divided by 0.0659. We need the density. Multiply that by the density of the oil and divide by 133.66. And the density was down here, 781. But we need it in pounds per cubic feet, 62.4 approximately. So what do we get? Anybody have a calculator or not? Okay, we got $11,057 standard cubic feet per stock tank barrel, and that's versus 11,000 and what was it from 11,014. Well, this number here isn't quite exact.
That was 2128. 2128. 21.8. The multiplying factor.
Oh, this should be 2128. Okay, yeah, that's a number that's more familiar. 2140 is 2128. And then what do you get here? What do you get here with 2128?
It's also with the 1998.
1099.
Yeah.
We say 11,000. Is that close enough? So, I mean, we're close enough for the 62. Should be 6242, I think. There's a few little things like that, but okay. So we're basically, we've got the same number for that. Okay, so the gas in place and the oil in place should be the same from the simulator and the PVT. Now we've got to see whether the recovery factors from the constant volume depletion is, let's see here, save this. Okay, so now we've got the recovery that we have to calculate. We can do that from these results. I'm going to close all of these windows here, and then what we'll do, we'll take a short break. But if so, I think that our initial gas in place, G, and the initial oil in place, N, these are the same between the two because we start with the same reservoir volume. We haven't completely checked that, but we've got the same initial GOR. Okay, that's basically from that. Now the question, as it depletes from 5,000 down, are we going to get the same number of moles produced and the split, the compositions and so forth? How are they going to compare? Well, in the simulator, do you see any difference between the reservoir simulator and the PVT experiment? What are some of the differences you see, or that you've noticed? Okay, what's one difference? The PVT simulator has no water in it. Okay, now does that really matter? There's no, in the simulator, there's no thermodynamics between the water and the hydrocarbons, right? But in the PVT cell, in the simulator, the PVT simulator, the constant volume depletion, what does constant volume mean? The hydrocarbon pore volume remains unchanged. But what about in the reservoir simulator? Huh? Yeah. It's got water. As the pressure drops, what's going to happen to the water? Expands. Okay. What about the pore volume? So let's look at the data set for the simulator. Okay, and this number here is the compressibility of the water. If I want my system to be like my PVT simulator, then you have to make that 0. Okay. What else do we have to make 0? Well, the rock compressibility has to be 0, right? Now the pore volume, the hydrocarbon pore volume, should remain constant in the simulator. Okay. If you leave those water in there, then what is going to happen to this behavior here? What will happen to the line, which is the model? With water, without water? It'll shift upwards because you're getting pressure support. Okay? Okay. And if I left it in there, which I usually would do if I hadn't wasted so much time getting where we're at now, I would actually let us be confused, because the simulator is going to give more recovery at a given pressure than is the PVT simulator. Okay? And you're going to think, well, it's not really simulating the same process. We're doing 500 PSI pressure drops. It's not, there's no relative permeability. Okay. But at least now we've eliminated the pore volume difference. Okay? And so what I'm going to do now is I'm going to get rid of this end. I'm going to run it for 10 years. See how far the pressure depletes. I don't know. I just want to see how far it depletes to see. Okay, average pressure is down. Okay, it depletes far enough down. So we've got 1,000 pounds here. We got 2,000. Here's 2,000 pounds, pretty close. So we've got a recovery factor at 2,000 pounds of 47% gas, 32.5% oil. Okay. Can somebody write those numbers down? So we've got 32.5, 47. So 32.5, 47. Oh, at 2011, that's recovery factor oil, recovery factor gas, and average pressure. Okay. let's increase the permeability to 1,000 to make less pressure drop in the reservoir. It'll be more and more like a uniform. Just curiosity. Okay, we got to find 2,000 on the pressure. So we got a little bit plus minus 2011. Okay, 33.1, 46.8. That was at 2021. So this is K 100, K 1000. Kind of gives you the magnitude of change. I mean, making it more and more. This is a little bit more than line thickness on the oil, but not too much. Depends how thick the line is. Okay. Okay. Then what we need to do is take the EOS out results and process those into recovery factor. Okay, we've got a little bit on this density of stock tank oil changing, but not too much. I think we're going to ignore that and just take these results into an Excel spreadsheet and do cumulative moles removed. We're going to separate that into surface gas and surface oil. We're going to add up the oils and up the gases, and when we get down to 2,000 pounds, we're going to find out how much of the original oil, surface oil and gas that we have produced. And those numbers will compare with these numbers here. Okay. Okay. Okay, we've got pressure, PSIA. Let's see this. This we don't need. This is moles produced, right? This is the mole fraction. We'll just call it the YSO. This is molecular weight, SO. And then we're going to go for a density, pounds per cubic feet. That's varying a little bit, but this is pounds per pound mole. Okay. And the density we're going to use is what? We had 7, 8, a little bit less than 7, 8, 7, 7, 7, 7, 5 on average. 7, yeah. We can study the sensitivity of that up there. I'll put that in red because that's something I can change if I like. We'll just fix 62.4 times that. Okay. So then we need to know what's the initial oil in place, and the initial gas in place. And to get that, we need here. We got this many barrels, but we need to know how many moles there are, right? And right now it only tells us the moles removed. So what we're going to do is ask for this also to give just the moles. I think it's just written like that. Okay. So we've got this many moles, 6.5061, 10 to the 7th. 6.5061, 10 to the 7th pound moles. Should we check that against what it has in sensor? I think probably is worth doing. Does it give moles somewhere? Okay, initial moles in place. Take all those together. Should that be right? Six, 4, 9. 65061. Close. Not completely happy with it, but six, 4, 9. And this was okay, 0.2%, that we can accept. All right. Okay, so then 65061, 10 to the 7th. Initial moles. Okay, and we've got then we need the gas in place and the oil in place. Okay, so that's equal to the moles times this, what, 1 minus this first fraction? That's how much turns into surface oil, times 379, right? 23 BCF gas. BCF of gas. Okay. And then we need to get the number of moles of the oil here. And that'll be the number of moles times the mole fraction times the molecular weight divided by the density. And that's cubic feet. So divided by 5.6146. So 2.11 million barrels. Pretty close. A fraction of a percent. Okay. Now the difference is this one here. So if we want it to be 2008, remember that should have been 0.78 something. It's getting closer. So it's a trade-off. It's having that magnitude of an effect. The densities here were 7811. We should be getting, the further we take this, the closer we get to the, so it's getting pretty close. Okay? So, now we have to calculate this oil produced, gas produced, MP, and the recovery factor of gas, recovery factor of oil. Like that. And to do that, we have to take the difference in Q here times so a little bit of the problem is that we've got this discretization. You know, basically we've got changes. And so what I'm going to do is I'm going to create an extra column here where I actually calculate an average mole fraction over the period. Okay? Insert. So this is going to be YSO average. Okay? And that'll be average. See, the way this is, just to sketch it, basically the CVD, the continuous change in basically YSO is like that from the simulator if you looked at the time steps there. And what this is going to do is that when it reaches the dew point, it's going to let's say it reached the dew point on a time step there, then it should be giving what we're taking is the equilibrium composition at this point here, and assuming that it's, I think it's going to be on the underside of this. I'm pretty sure it doesn't look like that, because these compositions we get from the CVD are the equilibrium compositions at the end of the time step. Okay, so I think it's something like that. So if we want to bring this kind of average up, we take the previous. See, how would we do that? Actually, this should be going like that. So how would we calculate that to be correct? We would take what we actually have plus the previous one and use that, I think. So I think we'll try that. Average of this to that. Okay. And then we'll use the moles produced in that increment times the average, except it's 1 minus this times 379, right? Okay. Okay, and then we've got the same thing. Moles times the mole fraction that becomes surface oil times molecular weight divided by density divided by 5.6146, something like that. These are actually D, PP, D, and P, like that. All right. And we take the previous plus the incremental. And then we take that and we use this. And we got 47% recovery of gas and 33% recovery of oil. Was that 47? I said 44. I said 47 and I wrote 40. That means we're getting tired at 2000. Okay. Okay. And that's the way it should be. Now, I don't know how many weeks last year you used to try to get this
So much.
process. Weeks at least. Individual groups all suffering through the same different kind of things. Now, all I can say is that we stumbled through it in 2.5 hours, and I realized that we had no breaks. Luckily, nobody had to go to the bathroom, I hope. At least I didn't. I'm the worst. And we basically went through several processes. We did the EOS consistency check. We did the surface processing. It's not easy. We ran into several problems. The two-phase split would have caused problems in consistency because sensor would not have taken this C4 plus oil, C5 plus oil. It would have assumed it was a single phase. whereas we would have had a problem getting from phase comp what that single phase property density was. A number of things like that would have been differences, so we had to kind of create something that was apple to apple, red apple to red apple comparison. This little thing on the integration helps because the discrete steps of 500 psi are clearly much bigger than in the simulator. There's a number of things like that. But at the end of the day, this plot reflects what I call a type curve of depletion recovery performance for gas condensate. It's independent of rel perm. If you don't believe me, you can take the data sets that I give you. You can change the rel perms. You can make your own sensitivities. You see, when he walks in the door, the lights go out. You know, this is a spooky guy. Okay. And it's a type curve. This curve reflects pure PVT. And the great majority of recovery performance, depletion recovery performance for a gas condensate is pure PVT. It is simply the carrying capacity of the gas to hold condensate in place. The equation of state may not predict it accurately. You probably don't know that's the case because when you do tuning in the equation of state, you fit liquid dropout, not the carrying capacity of the gas, which is composition. But the simulator giving you the same performance, the reservoir simulator and the PVT simulator, they should have the same kind of performance. And the way to make sure of that is to go through this kind of process. Now we can put back in compressibility of water, compressibility of rock, aquifer, layered performance, and everything else. But what you should know is that any cell in the model experiencing depletion is being controlled by the PVT describing that cell. And the only way to make sure that that PVT is describing it properly is to go through this kind of an exercise. Okay? It's also a nice exercise because you can study the effect of water, of rel perm, and so forth for your gas condensate. And anything that makes it deviate from these, call them the type curve, the PVT type curve of performance, recovery factor of gas and oil, making it better, making it worse. Basically, you have this reference behavior that goes back to the PVT data. If you have high quality PVT data, the symbols, you want to make sure that your lines go through those symbols as closely as possible. Okay? That's your PVT quality fit. I mean, it's the quality check on how well your equation of state describes the PVT data, which next week he's going to have to defend because he's been developing an equation of state for a gas condensate field in Colombia. The Colombians don't mess around. You screw up, the mafia. So he okay. So this plot, you don't get it in the PVT report. You have to create it yourself, and you can make the comparison and see. Okay. Well, if I lost anybody, then you have the unfortunate pleasure of being able to re-listen to the video when I hit this red button here.